Hi everybody. Let's take a few minutes today and try to understand the concept of what we call relative velocity. This is something that is pretty simple once you get your head around it, but it can be a little bit difficult to actually understand it, especially when we get into situations with two-dimensional motion. But let's just keep it simple and talk about 1D motion for now, one dimension. And what this idea is. Well, the word relative basically means that the way you measure someone's motion can be different depending on how you look at it. All right? So let's write that in English. The way that you measure motion can differ, and I'm going to say depending on the point of view you observe it from, or you measure it from. So that means that two people could measure the same thing, but if they were looking at it from a different perspective, they might get different ideas about how the object was moving. And what's more difficult to get your head around is the idea that it's impossible to decide who's right. Both of them are equally correct, which means that when you measure motion, if you have different points of view, you're always going to get different ideas, but you're both correct at the same time. So we have to be very careful when we measure motion about our reference frame and our point of view. So let's think about something else that's equally important. It is impossible for you to tell if you are moving with a constant velocity, that's an unchanging velocity, or if you are actually standing still. Staying still. Now you might think, wait a minute, sure I can tell if I'm moving, but let's be careful about it. The important words are moving with a constant velocity. So let's say you were, well, I can give you a perfect example right now. Right now, you're sitting at your desk or somewhere, and you're looking at your laptop, and you're watching this video, and you're sitting in your chair, and you're saying to yourself, I'm not moving. However, if I were to back up from this picture and go up into space and look down on you, I would see you, of course, you'd be very tiny, but here you'd be, say here, and you would not be standing still because the Earth is rotating, it's spinning, and in fact, at the surface of the Earth, you're going close to 1,000 kilometers an hour. And so I would see you rapidly going, zoom, like this. And I would say, no, you're not standing still or sitting still at all. From your perspective, or we could say, relative to you, in this picture, your velocity is 0. But relative to me, looking at you from a different point of view, your velocity is 1,000 kilometers per hour in sort of a curvy path, if we think about direction. So that's a huge difference. And of course, you don't know that you're moving. You cannot feel the Earth moving at all. In fact, many people would have argued in the past that the Earth can't be moving or else they would feel it. So what is the difference between feeling and not feeling moving? Well, the key there is that you can only feel acceleration. You can only feel it if your velocity changes. So imagine, for instance, If you've ever been on an airplane, and the airplane might be cruising along, so let's put here's the inside of the airplane. All right, there it is. And we don't need the wings, but the airplane is cruising along at a nice, constant, smooth speed of, well, believe it or not, airplanes can go about 1,000 kilometers an hour, jet planes. So let's say it's going 1,000 kilometers an hour. That's pretty darn fast. And here you are sitting in seat, J3, and you're just sitting there, enjoying the flight. And if you don't look out the window, and the plane is going along nice and smooth, you close your eyes, you wouldn't even know you were moving. In fact, you could get up from your chair, and you could walk to the back of the plane and use the bathroom, walk back to your seat, and in the meantime, the stewardess can come by, and she can drop off a nice little glass of pop for you, and your glass of pop is in your hands, and it's not spilling, and it's not splashing. You don't even know that you're moving, even though you actually are moving. But in order to see this motion, I would have to step outside of the plane and get a different perspective. I'd have to view you from a place outside of the plane. Now, when do you feel it when you're in an airplane? Well, you feel it when suddenly the plane changes its velocity. So perhaps there's some wind, and if wind blows sort of on an angle, say this way, then the plane will bounce and shake. And bouncing and shaking means that you're no longer going exactly 1,000 kilometers an hour. You might slow down a little wee bit, and you'll feel that. You might speed up a little wee bit, or you might change your direction a little wee bit. Even a direction change is a change in your velocity. So as the plane bounces and bumps along in turbulent air, you definitely feel that. It's the same as when you're in a car and you are driving along on a nice smooth road and it's quiet and you're on a long trip and you're tired. So even though the car is moving at about 100 kilometers an hour on the highway, as long as there's not too many changes in your velocity, you can fall asleep in the back seat, or I guess that would be the front seat. You could fall asleep in the back seat and not even know that you're moving. And you could hold your glass of Pepsi, you could drink it without a problem, eat your potato chips, even read a book. But every time the car hits a bump in the road, that changes the velocity of the car, even by the tiniest bit. And these tiny changes from bumps and things in the road, or if the wind blows a certain way, or if somebody who's driving happens to slam on the brake and change the speed, even a little bit, even if they just turn the steering wheel a small amount and shift the car's position, those are all changes in velocity. Remember, changes in velocities are accelerations. So we can feel acceleration, but we cannot feel constant speed. That's the weird thing. As long as the constant speed stays constant, we don't feel it. And that's critically important, because that's sort of the basis behind what we're going to talk about next. Now, here's a constant speed. Let's say the car was moving at 8 meters per second, right? Well, it's not changing. So on a graph, if we do a VT graph, we would have this little line at 8, not changing, no slope. Well, what's the difference between another line? Let's say the car was going faster. Let's say you had a different car that was going 15 meters per second. Well, in terms of the slope, no change. The slope is the same. And in fact, if I took a car that was standing still and it was right on the 0 line here on my graph at 0, well, look at the slope. It's exactly the same. There are no accelerations, which means that each one of these would feel exactly the same to you, and you would have no way of knowing what your actual speed was unless you could step outside of your situation and view it from a different perspective. So a constant speed of 15 is no different than a constant speed of 0, which is kind of the same way of saying that you can't tell if you're moving or not when constant speed is involved. You can only feel accelerations. Now, we have a lot of questions we deal with where it is constant speed, and we can make use of this very cool idea, and we can solve the problems more simply. So let's take a simple example of two objects to get our head around this. Let's say there are two cars. So one car is traveling this way, and you happen to be sitting inside this car. There you are. And this car is going 10 meters per second, sort of to the right in this reference frame. Now over here is another car, and this car is going to be moving the other way towards you at 8 meters per second. Let's think about how this might look depending on where you were. If I was standing here on the side of the road, I would see both cars moving. I would look at the first car, which has you in it right here, and I could measure that you were moving 10 meters per second. And I could look at this car, and I could measure it was moving at 8 meters per second. Relative to me, the velocities of the cars are what the numbers I have already written down, if I'm watching you from here. However, let's erase that. Let's imagine that it's you that's doing the measuring. Now remember, you're sitting in a car that's moving at a constant speed. So as long as you don't look out the window, imagine a car with very dark windows, or even if it's at night, as long as you don't have any idea from a different reference frame that you're moving, you cannot tell that you're moving. So if you were sitting in this car, you might think that your velocity was actually 0. And if your velocity was 0 and you thought that, then the motion of this car would change from your perspective. Because what happens to your 10 meters per second? If you don't know that it's there, then you only notice that motion when you look at the motion of the other car. Which means that it will look to you as if this car is moving with 8 meters per second plus 10 meters per second, and it will look as though it's coming towards you at 18 meters per second. That would be called the relative velocity of the cars from your perspective. And in fact, it would also appear as if the direction of that was to the left or towards you. Maybe towards you is a better way of describing that if it's from your perspective. The car is coming towards you. Okay? In other words, this way. But now, if we view the same picture, and instead we take your friend who's now sitting in this car, they would say, well, they cannot tell that they're moving without looking outside. And so to them, it's like their velocity is not anything at all. It's like a constant speed of 0. And when they look at you, they see your car approaching, and guess what? They see 10 and 8. And they see your car getting closer at 18 meters per second. So they do see the same speed, but they would argue with you that you're not moving left, you're moving right. And so the direction would look different. They would say, no, you're going this way. And those are two different velocities, aren't they, if we count direction? So who's right? Well, the truth is, it's all right. And it all depends on which perspective you're looking from. So things can look differently from different perspectives. And that's the idea of how relative velocity is supposed to work. So another example, just to give you, imagine you're running. And if you're running, but you happen to be running on a conveyor belt, something like they have at some major airports. It's like a moving sidewalk. And if the moving sidewalk is moving this way at, let's say 2 meters per second, but you happen to be running this way at 4 meters per second, well, let's erase this other stuff so it doesn't confuse us. Well then, how would this look? Well, if you were sort of confined on the conveyor belt and you were all encased in black walls all around you, so you couldn't use other perspectives. You couldn't see another reference point. you would not notice that the conveyor belt is moving. You would not be able to tell that there's 2 meters per second of moving conveyor belt because you can't see anything except the conveyor belt. Just like on the Earth, we cannot see that we're moving 1,000 kilometers an hour as we rotate because we don't have a perspective away from the Earth. Which means that if this is like a 0, you're going to think you're moving at 4 meters per second to the right. So we would say that relative to you, your velocity is 4 meters per second to the right. But if we change it up so that I'm watching you from a different perspective, let's erase these lines. If I'm watching you from the side and I can see both things, if I can see the conveyor belt and I can see you, then I have a different perspective, right? A different reference frame. What I will see is I will see a combination of this. So relative to me, I'll be the green one. What I would see for your velocity is a combination of 2 left, which we'll call -2, and 4 to the right, which we call +4, which means you're only going to look like you're going 2 meters per second to the right from my perspective. I'm going to see your speed to be 2, and it's going to be a direction to the right. So you see how it's 2 different answers. And you can see how this can be quite confusing. And so that's the idea of relative velocity. Another common place where relative velocity shows up is when you are moving in the water. If you have a boat and you try to paddle this way, but the river that you're paddling in has a current this way, then what will actually happen is you will move downstream. You will drift this way without knowing it. Or you'll know it if you can see the shore, and you'll land way down here. You were aiming for this spot, but you ended up off course because you drifted with the river. Now, notice up here how when I figured out your velocity relative to me, I added the 2 velocities that I could see. I added the conveyor belt velocity to the left as -2, and I added your velocity as 4. And that told me the new velocity that you would have relative to me. So now, let's take this same picture and do the same thing, but we'll do it with the 2-dimensional water, except this time I'll just draw it from scratch. Okay, let's do that again. Here's a boat. If you were to paddle straight across this way, trying to get here, but the river had a current like this, then what I would have to do, let me call this the velocity of the river, and we'll call this the velocity of your paddling. Then if I stand here on the shore, then the velocity relative to me, R, we'll call it the relative velocity that I would see, is 2 different velocities added together. I would see the velocity of the river, and I would see the velocity of your paddling. And so we would have to add those together. Now, interestingly enough, the way you add like this is by taking this vector and moving it so that it's tip to tail with the other vector here. And then you would have to find this line here, and this blue line would be actually representing the velocity of the paddling plus the velocity of the current, tip to tail. We add the vectors, and of course we use our triangle math in order to figure out questions like this. So that's what it might look like in 2 dimensions. So that's relative velocity, and hopefully you can get your head around that and how we can use it to solve some more complicated problems. In another video, I'll give you some examples of how we use it to solve problems more simply.